Okay, today we're going to start talking about how to transform linear equations, or basically how you can take the graph of a particular function and kind of move it up and down, left and right, or even stretch it and compress it a little bit. Now, I'm going to try to make this as simple as possible because it can be a little bit confusing right away if it's not something that you have done before in the past. So we're going to transform these, and then there's going to be a little bit of problem solving. I'm not going to get into that a whole lot because it is fairly self-explanatory if you understand how you're supposed to go about transforming the functions to begin with. Alright, now essentially to start with, there's four different things that we're going to talk about. How you can shift something horizontally, how you can shift something vertically, and then how you can reflect across both the x-axis and the y-axis. Now, starting with the horizontal shift, basically what you're doing is you're changing the input value for your x's. Alright, so what happens when we do that is, going back to the whole function thing, we're going to take and we're going to fill a value in with x, either plus that number or minus that number, which helps move us left or right. Now, the thing that's a little bit backwards about this is if you want to take your graph, like this blue line that's in here, and you want to shift it to the right, you actually have to go minus however far you want to move it, and it moves it right, as opposed to the plus that you normally think it'd do. If you put x plus some number in for x, that actually takes and moves your graph back to the left. Alright, so when you're dealing with moving things in an x direction or reflecting things across like the y-axis where you're changing your x values, things are a little bit backwards. Okay, now shifting something up or down, basically you just take however many units you want to move something up or down and you add it to a function. Okay, and this will make a little bit more sense once we get into this a little bit. Okay, then you have reflections across the y-axis and the x-axis. The y-axis, if you think about this, essentially you're taking this x value, say call it 3, and you want to make it -3. Alright, so you're just simply taking the x values that you fill in and you're making them negative, okay, which switches things about a little bit. When you reflect across the x-axis, essentially you're changing the output values. Instead of ending up with a value that's up there, you end up with a value that's down there. So basically you're taking your entire function, you're taking the output value and you're making it negative after the fact. Okay, now this is kind of just a little bit of a saying in here that's supposed to help you kind of remember how to think about vertical and horizontal translations. Okay, so if you add to the y, you're going to go high, okay, meaning just simply at the end, if you add to your function, it's going to move it up. Same idea could be said if you subtract from it, it's going to move your function down. If you move to the x, and this is kind of what we talked about, if you add to the x, it actually takes you back in a left direction or a negative direction, as opposed to subtracting that number when you fill it in for the x value, you move to the right. Okay, so this is how we're going to start. Okay, so it says let g of x be the indicated transformation of f of x. Write the rule for g of x. Okay, so we're given an original function. It says f of x equals x minus 2. And it says we want a horizontal translation, meaning we're going to move it left and right. In this case, we're going to go right 3 units. Okay, so basically what I'm going to do is in place of the x, I'm going to take x minus, and we want to go to the right, so I'm going to go x minus 3, and I'm going to fill that in place of my x. Alright, so in place of the x, I'm going to have x minus 3, and I'm still going to have minus 2. Okay, so again, when you're moving things to the left and right, you're changing the input value. Alright, so instead of just having this x here, I'm going to take my desired translation and fill it in there. Again, it's opposite. If I want to move 3 to the right, alright, I actually subtract 3 and I fill it in. So I'm going to find f of x minus 3. So when I fill that in, my final function ends up simplifying to being x minus 5, which in this case I'm going to call g of x. Okay. Now what you will see as we move forward here a little bit, and I don't necessarily have a graph of this up there, all right, but if I were to think about this, this is kind of just going to be a makeshift graph here over on the side. Alright, but if I take my two functions, alright, first of all I have x minus 5. Alright, so I'd be down here as my y-axis, and I would go up 1 over 1, up 1 over 1 to figure out where my translated graph is. That would be this one down here. Okay, now on the other side of things, if I take my original, the x minus 2, alright, I would go down here and then same thing, up 1 over 1, up 1 over 1. Now you'll notice that they are parallel lines, alright, but if we think about this value right here, 1, 2, 3 roughly, over there you can see how it is translated 3 units to the right. Okay, everything on this line right here, my left line, the other line is just a matter of moving 3 spaces to the right. Okay, now here's another idea of what we got going on. Okay, but in this case, we're not given an original function. We have to find that function using some of the stuff that we talked about in the last section, and then we have to figure out how we're going to take the function that we're given based on the information that we're given, and how we can take that and reflect it across the x-axis. All right, which is fairly similar. You're taking the y values of your original function, you're just flipping them down and reflecting over that x-axis. But first things first, I have to figure out an equation for the information that I'm given. Okay, so going back to what we talked about in the previous section, or the previous sections, all right, I need to find a slope based on the information that I'm given. So if I'm going to find my slope, I'm going to take the changes in the y's over the changes in the x's. So I'm going to take just this point and this point to start with. So my y's, I'm going to go 1 minus 0. And remember, I have to keep with the same order, so I'm going to go 0 minus negative 2. Alright, and I'm going to get a slope of 1/2. Okay, now I'm going to use the slope-intercept form idea to figure out what my equation is, not the point-slope one, because I think this is a little bit easier. So in place of the y and the x, I'm just going to take a point. Okay, so I'll just take this first point again right here. I'm going to fill 0 in for the y, 1/2 in for my slope, negative 2 in for my x, and I'm going to solve that for b. So 0 over here, this is going to become negative 1 plus b, so I'd have to add 1 over to the other side, and b is going to equal 1. So after it's all said and done, the equation, which we're going to call f of x, okay, we'll just take that y and make it an f of x, alright, is going to be 1/2 x plus 1. That is the equation of the line that I get based on the information represented above. Now, we're supposed to take that and write a rule for g of x, which basically takes this information that I just found and reflects it over the x-axis. Now, if you remember back to the beginning, what we talked about, reflecting across the x-axis essentially changes our output values. So we take our original function, and to reflect it, we basically take and make the entire function itself negative. So g of x in this case, in order to reflect it, I'm just going to take that entire function that I had before, and I'm going to make it negative. So essentially, the equation or the rule that makes this reflect across the x-axis looks like this right here. Okay, negative 1/2 x minus 1. And you'll notice that everything in there happens to be the opposite of what I started with up here. Okay, and essentially what would happen with something like that is, and this is kind of just generalizing, but you'd have a line that goes up and over like this for your f of x value. This time around, you would have my g of x line going back there. If you think about it in terms of the coordinate plane, and that's not necessarily exactly where it will be on the coordinate plane, because we have different y-intercepts and just being at 0, 0. But you can notice how if you would take these graphs and you would fold them over the x-axis, they would lay on top of each other, meaning they are in fact reflections of one another. Alright, and this gives you a better idea of what those would look like, as opposed to my kind of makeshift graph there. you can see how your y-intercepts are 1 and -1 instead. But you can see how, again, if you were to take and fold this graph right along the x-axis, these lines would lay on top of each other, showing that they are truly reflecting over the x-axis. And again, if you were to take points up here, let's see, 1, 2, 3, 1, well, it's kind of hard to tell with that, so I won't worry about that. But basically what should happen is you're going to have the same x value, all right, but your reflection is going to have an opposite y value. So if you have the point up here that happens to be 1, 1, the corresponding point down here is going to be 1, -1. Okay, again, we just changed our output value when we reflect across the x-axis. Okay, now the other two things we can do is we can stretch and we can compress something. Okay, if a line becomes steeper, then it means it's been stretched vertically or compressed horizontally. If the line becomes flatter, then it means we have compressed vertically or stretched horizontally. All right, now same idea what's going on here. If you look at the way this is going to work, stretching something vertically or compressing it vertically is a lot easier, because you're just going to take your function that you start with and you're going to multiply it by a factor, all right, that either makes it bigger, stretches it, or it shrinks it and compresses it. The thing to remember about this is if you have a number that is greater than 1 that you multiply by it, okay, it's going to stretch it away from the x-axis, so it's going to essentially pull it up. Okay, if you have a fraction, it's going to compress it towards the x-axis, so you're going to flatten out a little bit. All right, over here, a little bit different. Again, you're changing the input value if you're thinking about horizontally doing things. So wherever your x is, you're going to take and you're going to multiply your x by 1 over whatever the factor is that you want to stretch or compress by. Okay, now because it's kind of an inverse looking input that we're throwing in there, if b, or the number that you're going to stretch or compress by, happens to be greater than 1, okay, we're going to stretch away from the y-axis. So in other words, it should flatten out or move away from the y-axis a little bit. If the number that you fill in happens to be a fraction that's between 0 and 1, you're going to compress towards the y-axis, so your graph would actually move in and flatten out a little bit. All right, but again, that'll make more sense once we actually get into this particular, an example that kind of explains that. Now, it's important to remember that there's a couple things that don't change. If you stretch horizontally or compress it horizontally, your y-intercepts do not change. Okay, and if you stretch something vertically or compress it vertically, your x-intercepts don't change. Now, thinking about that in your head, you might not really understand, but it'll make more sense once we get into an example. Okay, so g of x in this case is supposed to be a horizontal compression. Okay, now if you don't remember the difference between compression and stretch, that's okay. You'll understand it as you move through here. So we're given an original function right here. Okay, now we want to compress or stretch it horizontally, so that means I'm going to fill in place of the x and multiply that by 1 over whatever we want to stretch or compress by. So in this case here, my b that we talked about in the previous slide is going to be 1/2. All right, so what I want to do is essentially take f of 1 over 1/2 x. Okay, or basically, if you take 1 and divide it by 1/2, you basically get 2. So f of 2x is more or less what you're going to find. And that, again, that just comes from taking the 1 and dividing it by 1/2. Okay, so what this tells me I'm going to do is, again, I'm affecting my input value. All right, so in place of the x right here, I'm going to fill in this 2x. So the negative sign still stays there, so I'm going to get minus 2x plus 4. Okay, now after we made our translation, remember, we are looking to call this new function g of x. So I simply just write g of x equals what we found up here, e minus 2x plus 4. Again, it all comes down to what are you trying to compress or stretch by. Okay, we call that our b, and then 1 over that, and we fill that input in with the x, and that helps us move things horizontally, okay, because we basically changed our input value. Now again, this is kind of what we're looking at right here. All right, f of x is our original function, okay, which is in blue down here. All right, and you will notice that when we take and we apply the horizontal, in this case, compression, all right, we had a factor of 1/2, which takes our graph and it brings it closer to, closer to the y-axis. All right, and what you will notice for the most part in this case is you compressed it horizontally a little bit, right? And your y-intercept really hasn't changed a whole lot when you look at that. Okay, now vertical compression's a little bit easier, all right, because we don't have to worry about input values so much. We just have to worry about if I'm given the function f of x equals 3x plus 2, and I want to apply a vertical compression to that, I'm simply going to take this whole function times whatever it is that I'm going to compress it by. So in this case, 1/4. So 1/4 f of x, I'm going to take this and I'm going to multiply it by 1/4. So my g of x, or the function that I'm just naming this so we know it's different, is going to end up being 3/4 x plus, if you take 2 times 1/4, you get 1/2. Okay, so the vertical movements, both just shifting it up and down or compressing it, are a lot easier because essentially you just take the entire function you're given and you just get to multiply it by a certain factor. Okay, now again, blue is our original f of x function. After we vertically compress something, okay, we end up with our g of x function. All right, and as you can see, we have shifted our values a little bit away from the x-axis or closer to the y-axis. But our x-intercept in this case has not changed, as opposed to the last time when it was our y-intercept that didn't change, when we were talking horizontal things. Okay, now the last thing that we're going to talk about is what happens when you have more than one thing that's being applied in order to transform a function. Sometimes you'll have a vertical horizontal compression, and that'll be matched with some type of translation as far as moving it left and right or up and down. Okay, so in this case, we're given our original function, and we want to go ahead and shift that 6 to the left, and then we want to stretch it horizontally by a factor of 4. So the first thing that we're going to do is we're going to move it left 6 units. Now remember, we move it left and right horizontally, it's a little bit backwards. All right, so instead of actually saying I'm going to subtract 6, I actually have to go opposite. So I want to go f of x plus 6, which remember, plus 6 means I'm actually going to move it back to the left. All right, so I'm taking this function up here and I'm filling x plus 6 in for x. So it's going to look something like this. So when I'm done with that particular transformation, I'm going to end up with 3x plus 18. Okay, so that takes care of moving things left 6 units. And then we need to have a horizontal stretch by a factor of 4. Now if you remember again what we were talking about, we take whatever our factor is and we call that our b. Alright, so we want to find, in this case we'll still call it f of x to begin with, but this will just be our new f of x after that translation. So f of, we would say 1 over b, well in this case 1 over 4 times x. Alright, so we want to, again, the b is our factor, we put it on the bottom. So what this is telling me to do is we're changing our input values again horizontally. Alright, so in place of the x, I'm going to put 1/4 x, and the 18 is going to become unchanged. Okay, so again, our y-intercept hasn't really changed when we do this. Okay, so if I do the multiplication here, and again, we're going to call the finished product here g of x, 3/4 x plus 18 would be the new function that represents a horizontal shift of 6 to the left and a horizontal stretch by a factor of 4. Okay, now I don't necessarily have a graph up here of what this is going to look like. Alright, and you could graph this on a graphing calculator if you wanted to, but again, if you think about what we originally started with, f of x equals 3x, we'd have something, in general that's going to go through the origin and go up with a slope of 3. Now in this case, if we take it the next one, we're going to be looking at plus 18 as our y-intercept. So obviously you'd have to think in terms of a scale, and then we go up 3 over 4. So it's going to flatten out a little bit. All right, and again, this isn't drawn to scale so much, but we have horizontally stretched it out, all right, or basically pulled it away from the y-axis. And you can also see how, if you think about stretching, or excuse me, moving things left and right, we've taken this graph, and you can see wherever my y-intercept, or excuse me, my x-intercept ends up is going to be down here somewhere along the line. Okay, so we have in fact moved things to the left as well. All right, and this will be easier to tell once you get to your assignment too. It'll be easier to graph and kind of see what's going on as far as that's concerned. All right, very last one that we're going to talk about is we are going to apply a vertical compression of 1/2 and a horizontal shift of 8 to the left. Now, I usually like to do the shifting first, and I know this has it written in the opposite way, but I'm going to go ahead and I'm going to say if I'm going to shift it 8 units left, that means I'm going to have to take and find f of x minus 8. All right, which basically means if my original was just this, I'm just going to end up with x minus 8 in place of that x. Okay, and then a vertical compression, we're simply going to take what we have right here, and we'd be taking 1/2 times whatever the function is we have at the time. So 1/2 times x minus 8. All right, and again, we're going to call this new function, or the finished product, g of x. So 1/2 x, and if you take 1/2 times -8, you get -4. All right, so again, this would be the finished product of what we have going on there. Now, it's important to remember when you go through this, if you can understand the rules as far as shifting things horizontally or compressing things horizontally, it involves filling in place of the x. All right, whether it's a factor that we have to multiply by, or 1 over a factor we have to multiply by, or simply just minusing some number to move things to the right, or adding a number to move things to the left. I think those are the most difficult. The vertical translations, as far as adding something or subtracting something from the function to move it up and down, or even multiplying an entire function by some factor to stretch or compress vertically, is much easier. All right, so assignment, just as usual. If you have any questions, please just make sure that you ask, so we make sure that everybody's on the right page as we go through this.